Chapter 11 will be going over chemical bonds and periodic trends of the periodic table. Let's talk a little bit about metals and nonmetals and metalloids. So in metals, they tend to lose electrons and they form cations. Nonmetals are the opposite and they tend to gain electrons and form anions. Metalloids can have properties either metals or nonmetals. They're kind of in between. And our periodic table is broken down to where we have metals on the left side of the periodic table and nonmetals on the right side, and then we have metalloids in between the metals and nonmetals. In general, atomic radius will actually get bigger, increases as you go down a group, and it decreases when you go from left to right across a period. So as you go down, it gets bigger this way, and as you go right, it gets smaller. The reason is because this over here, we're having more and more layers of electrons, the level n. This is level 1, 2, 3, 4, 5, 6. It gets bigger and bigger. Orbitals are getting bigger. But as you go from the left to the right across a period, what happens is you stay in the same level of electrons, but you have more and more protons as you go to the right. And protons will pull the electrons closer, resulting in a smaller atomic radius. So again, we want to say when we go down a group, n quantum levels are added to energy levels. So electrons are getting further from the nucleus, so size increases. Across a period, the n remains constant, same level of energy, so same level of orbitals, but atomic number, which is number of protons, is going up. So it pulls the electrons closer together, resulting in a decrease in the radius. Next, we want to talk about ionization energy. Ionization energy is the energy required to remove an electron from an atom. So for example, if you have sodium atom, if you put in some energy, you can remove an electron out of the sodium atom and you can make a sodium cation. So this is called the first ionization energy because it's energy needed to remove the first electron from the atom. If you wanted to remove the second electron, it would be called the second ionization energy. That means after you pull out one electron here, you take Na plus and you pull out another electron from Na plus here, and then become Na2 positive. Successive ionization always increases in energy as the remaining electrons experience stronger attraction to the resulting cation produced. So it's always going to be harder from the first to the second to the third to the fourth level. Looking at the first trend for ionization energy, we want to talk about the first ionization energy. In general, it's actually the opposite of the size trend, where if the size is bigger, it becomes easier to remove the electron, so the energy is lower. So in this case here, it goes down, ionization energy, the first level, goes down as decreases as you go down a group. So go down this way. It gets easier and easier to remove the electron because the size is bigger. When the size is bigger, the protons have a harder time to reach the furthest electrons to hold it close together. So it's easy to lose electron. Now, if you go from the left to the right across a period, it gets harder and harder to remove the electron because the nonmetals love electrons, especially if you see fluorine. Fluorine loves the extra electrons. It's not going to let you remove the electron easily. And noble gases definitely will not let you remove the electron because they're going to hold tight to their perfect configuration. So remember, ionization energy for the first level, it decreases as you go down a group, increases as you go across a period, the opposite of the atomic radius trend. So just to recap, ionization energy goes down a group, decreases as you go down a group, and it increases when you go from the left to right across a period. And the reasons are, when you go down the group, the size gets bigger. It's easier to remove the electron because the protons are further away from the electron. If you go across a period to the right, what happens is the size is smaller now and the protons are increasing, so it actually holds the electrons a lot tighter together, making it harder to remove those electrons. Let's take a look more into ionization energy as you go further in successive levels of it. So if you go to remove an electron from hydrogen, you remove the first one. That's the energy needed. For helium, it's harder to remove, so it's to remove electron from noble gas, so it's going to be a high energy. But the second electron is even harder. So as you can see, successive ones are harder. Now if you take a look at lithium, the first electron is pretty easy to remove. The second electron is really hard to remove, from 520 to 7,000. That's because after you remove the first electron, the second electron that you have to remove actually already looks like a noble gas. It looks like helium, so it's going to be really hard to remove that extra electron away. And you can see here, as you go further to the next level, it's even harder. But the biggest jump that's obvious is when you see from an easy to remove to a hard to remove, is always because you've removed the valence electron, and this is the inside level where it looks like a noble gas here. So for beryllium, you'll have two that you can remove on the outside, and then the third electron will be what looks like helium, and it's a lot higher. See, almost 15,000 compared to about 2,000. So as you can see, as you go up the level, it always increases. But once you hit the inside layer, once you remove all the valence here, the third electron here tells you this is the inside layer, the noble gas configuration. It's going to be super big jump here. Okay. If we look at boron, we'll see the first level is easy to remove, first electron. Second electron gets harder, third electron gets harder. But then when you reach the fourth level, the fourth electron, it's super big jump here. That's because boron has 3 valence electron, and the fourth electron will be really hard to remove because it's on the inside layer. And you can see here carbon is in group 4, so the first 4 is fairly easy, just gets harder and harder. But then when you want to remove the inside layer, the fifth electron, it becomes super big jump here. So this is going to be helpful. If you saw a trend like this, you can tell if the big jump is between 4 and 5, you know it had 4 valence electron. If the big jump happens between from the third to the fourth one, the fourth electron is really high, so that means it had 3 valence electrons. Let's take a look again at electron configurations. We want to take a look at all the noble gases here, why they're stable. So over here, helium is 1s2. Is the only one that has 2 valence electron. Everybody else has 8. Okay, so the 8 for argon is in level 3. For neon is in level 2. Let's take a look at krypton. Krypton will be having its valence at level 4. Xenon at level 5. Radon at level 6. So these are just the inside layers of the electrons. So let's take a look at ionic bonds between Na and Cl. So we've talked about how Na becomes an Na plus ion, right? And we also talked about how Cl can become Cl negative ion. But right now we can actually show you the electron configurations. So what happens is they want to look like noble gases. So sodium turns itself to sodium plus because that's the same as the noble gas configuration in level 2. See that? So it's really stable then. And chlorine does the same thing. It gains an electron to do the 3s2 3p6, just like a noble gas for argon, and becomes Cl negative ion. Now when you have sodium plus and Cl negative, now they can combine together to make an ionic bond. So we can take a closer look again. Ionic bond is the attraction between the opposite charges. We could say that if sodium were to lose an electron, And a chlorine would take the electron. You can have a sodium plus and Cl minus, and they'll be bonded together using an ionic bond, which is an electrostatic attraction between opposite charges. You don't have to memorize this, but here's an interesting look at how NaCl is actually combined together in a solid state, crystalline form. Each Na plus is surrounded by 6 Cl ion. Each Cl ion is surrounded by 6 Na plus ion. So you can see that's how they're arranged like this. Let's talk about cation and anion sizes. Cations are always going to be smaller than the atom. Anions are going to be bigger than the atom. So if you look at Na and Cl, Na ion is smaller than Na atom. Cl ion is going to be bigger than a Cl atom. Okay, so let's take another closer look. If you take a look at cations here, they're all smaller than the atoms they came from. The reason why these cations are smaller is because we removed an electron on the outside, and now they have noble gas configurations, which is actually a little smaller because the outside layer is missing. On the other hand, if you take a look at the anions are always bigger than the atom it came from. The reason is because you are adding an electron in here, you're adding electrons in, and electron-electron repulsion, because they're the same charge, will force it to get a little bigger. So the anions are always going to be bigger than the atom it came from. So earlier we were looking at NaCl. We can actually look at other kinds of ionic bonding as well. So let's take a look at Mg. Mg will be Mg2 plus because it loses 2 electrons. And then you have Cl. Cl will gain 1 electron, so you'll need 2 Cl ions to pair with 1 Mg cation here. So if we were to take a look at the cation and anion drawing here, you can see the electrons are given up, the two valence, and they're receiving it. So you have 2 Cl anion and 1 Mg2 plus to combine to be MgCl2. We can also take a look at aluminum and oxygen, where you have aluminum will need to remove 3 electrons, right? So, and each oxygen can take in 2 electrons here. And then so you need a second aluminum to remove another. So altogether you have 6 given away and 6 received. So you get 6 positive ion and 6 negative ions here. It's actually easier to look at charges, but the charges do stem from the electrons transferring. So here's just another way of viewing how ionic bonds can be made. So let's predict ionic formula compounds. What we want to do between barium and sulfur. Barium is in group 2, so it will be 2 plus. Sulfur will be group 6, will be 2 negative. So when you combine 2 plus and 2 negative, you get BAS. We already knew that, so just make sure that they have the charges that are the same. So you can have all kinds of different combinations. If you have lithium and oxide, you need 2 lithiums to 1 oxygen because oxygen is 2 negative. So same for all the group 1s here. Okay. And then if you have chlorides, Cl negative and Li plus, you just 1-to-1 ratio. So same pattern for the rest of group 1. Bromides are also 1 negative. So 1 plus 1 negative, you can combine as is. Now sulfates is 2 negative charge. So you need 2 lithium to combine with it, so you would write the same for the other guys as well. So what is the formula for potassium phosphide? Potassium is K plus, phosphide is in group 5, because from phosphorus, so it would be P3 negative. So if you have 3 negative and 1 K plus, you would need 3 of the Ks to balance out the phosphide. So in this case, you have K3P. Now, if you have sodium sulfide, sodium is Na plus, sulfide is S2 negative because it's in group 6. So you would need 2 sodium to combine with 1 sulfur, so it'll be Na2S. Now let's take a look. What is the formula for magnesium nitride? Magnesium will be Mg2 plus, so let's write it down. Nitride is in group 5, so it's 3 negative. So if you were to combine them, you do the crisscross, you would know that it's Mg3 and 2. So our answer would be C, right there. Alright, so let's take a look at covalent bonds. Covalent bonds are different than ionic bonds because ionic bonds are transferring electrons and then making ions and then pulling them together by electrostatic charge attraction. Covalent bond actually share the electrons. Instead of giving up and receiving, they're just sharing it. So if you were to look at H2, you have each individual H, 1s1, 1s1, combine them together, you have overlapping s orbitals, you make a bond, and this two electrons here make one bond. So they're sharing the electrons here. Now let's take a look at Cl2 bonds. You have Cl. Cl has p orbitals because if you look at the electron configuration in Cl, you have level p there. So your p orbitals from each Cl, they're going to combine right there. So when you combine them, they become a pair, like a bond right here. So to draw that bond, we signify with just 2 electrons, or sometimes we just draw a straight line through. So here are pictures of more bonds here. Hydrogen, single bond. Fluorine is also a single bond right there. Bromine also has a single bond. And iodine has a single bond. All the other guys, the electrons on the outside here, are not bonded, so they're called lone pairs of electrons. So to differentiate between bonds and lone pairs, sometimes most of the time actually, we just draw a line where there is 2 dots between atoms like that. So we draw them like this. Okay, so a lot of times I prefer to draw it like this, where the bond is a line and the lone pairs are left as dots around there. And then here's the single bond, these on the outside are lone pairs. So that's 1 lone pair, 2 lone pair, 3 lone pair, 1, 2, 3. So each one of them has 3 lone pairs and 1 shared bond for iodine anyway. So sometimes we also have double bonds and triple bonds. So double bond just means in between these two guys here, there's actually 4 electrons. So each 2 electrons become 1 line. This triple bond here means there's 6 electrons. So 2 electrons, 2 electrons, 2 electrons. You have a triple bond right here. And these guys are the lone pair. 1 lone pair, 1 lone pair. Okay? So let's talk a little bit more about bonding. So when we talk about bonding, we have 2 kinds of bonds. We have ionic and covalent bonding. So the first thing you see is we have bonds. Okay? We have ionic and we have covalent. Now, under covalent, there's actually another 2 categories where we have polar covalent or non-polar covalent or pure covalent. They call it the same thing. Okay? So that's where this way it goes here. So I gotta erase what I just wrote there. Make sure we know about where the categories are. Okay? So we have on one side we have the polar we have the ionic bond where you have a metal and non-metal. And then you have these 2 guys here. They're both non-metal. They're sharing electrons, but one's polar covalent, one's non-polar covalent. Polar covalent is sharing electron lopsidedly because chlorine loves electron more than hydrogen, so this one holds more electron, that one has very little electron density. Hydrogen and hydrogen, they're equals, so they share evenly, so they're purely covalent character, or we like to call it nonpolar covalent bond here. Okay, so remember, ionic is completely the opposite, where you don't just share it lopsidedly. This guy takes all electrons, and this guy has no more electrons. Well, valence electrons anyway. So in the previous slide, we were looking at the different kinds of covalent bonds. One of them was polar covalent, one of them was pure covalent, right? So this is an example of why there's a polar covalent bond. It's due to electronegativity. So electronegativity is a measure of how much an atom likes electrons, so how much it's able to attract electrons in a covalent bond. So if you look at Cl here, Cl actually is in group 7, so it likes electrons a lot more than H does. So what happens is it gains most of the electron density on the Cl side, where hydrogen has a very small electron density on its side. So what you have here is a single bond here, but most of the electron density is on the chlorine side, a little bit on the hydrogen side. So hydrogen is partial positive, chlorine is partial negative, so it makes it a polar bond right here. So this is a polar covalent bond. And that's because chlorine is more electronegative, or it loves electrons more than hydrogen. So let's check out more on electronegativity. We have a periodic table worth of it. We have scale of relative electronegativity that's being developed by Pauling here. So the most electronegative element F, fluorine, is assigned a value of 4. And then everybody else we kind of like underneath 4 because they're all less electronegative than F. The more electronegative it is, the more it likes electrons. So the more it will pull the electron towards its side. So bond polarity is because basically one of them will pull the electron density more than the other. So it'll be uneven sharing, causing a polar covalent bond. If they share it equally, like the same strength, same electronegativity, then the bond will be nonpolar covalent. So electronegativity increases from left to right, because they love electrons more and more as you go to the to F. And as you go down a group, electronegativity decreases because it's harder for them to hold on to the electron, much less pull all more electrons because the sizes are getting bigger. So let's talk a little bit about polarity here. So we got 3 kinds. Obviously, we have ionic, and then we have covalent, and then under covalent we have pure covalent, nonpolar covalent, or polar covalent. Okay, so the difference between electronegativity, you have 2 atoms that you can make a bond, right? So if the bond has a very small difference here, so between 0 to 0.4, the bond will be considered nonpolar. Okay, if they're higher than 0.4 but less than 2, so between 0.4 and 1.9, or 0.5 to 1.9, right? This is considered as not uneven sharing, so it'll be considered polar covalent. Okay, now if it's 2 and higher, then it'll be considered ionic. So right here, if it's 2 and higher, it'll be considered an ionic bond. So over here you can see, so if you were to draw it out to divide, so pure covalent here will be from around 0 to 0.4, right? So right here will be nonpolar because 0 to about 0.4 in difference. So these are difference in the electronegativity numbers. So earlier you see like F had a 4 and everybody else has smaller numbers. So if you look at F and F, 4 and 4 literally would be no difference. So the difference here will be 0. F and F will be actually a pure or nonpolar covalent bond at a 0 right here. Okay, but if you look at H and F, it'll be different, where because now you're somewhere in the polar covalent zone, but you're not ionic yet, because to cross over ionic, you need to go to 2.0. Okay? All right, so let's take a look more at our numbers for the electronegativity. So let's take a look. More examples here. Nonpolar covalent bonds are going to be very small or no difference in electronegativity between the two atoms. So if you look at N and Cl, okay, N is going to be 3, Cl is also 3, so this bond is going to be a nonpolar covalent because the electronegativity difference is 0. So when you take a look, you have other options of nonpolar, H2, H and H, Cl and Cl. We also talked about F and F. Those guys all have electronegativity of 0, so they are nonpolar molecules. HCl will be different enough in electronegativity difference that you have a polar covalent. And ionic compounds, Na and Cl here, this is going to be a really, really big difference, higher than 2. So polar covalent examples, we have P and O. P is going to be 3.5, O is 2.1, so the difference is 1.4. So we know that O is more electronegative than P. So the arrow points towards O. That means O holds more electron density than P will. Okay, if you have N and C, N is more electronegative than C. 3.0 versus 2.5, the difference is 0.5. It's still polar because between 0.5 to 1.9 is polar. So N holds more electron density than carbon. And you see the arrow points towards N. So if you were to draw the partial positive and negative, you would say that this guy here is partial negative, this guy is partial positive. Same thing over here, oxygen will be partial negative, P will be partial positive, just within that bond right there. Alright, let's take a look at these numbers here again, okay? And let's say which one would form a polar covalent bond. So if you take a look at Be and F, Be is actually a metal and F is non-metal. So that's going to be an ionic bond. We don't have to worry about that. That's not going to be a covalent bond. Na and O are also going to be ionic because Na is a metal, O is a non-metal, right? So these two are ionic. The difference in electronegativity are really, really big. F and F is a covalent bond, but 4 and 4 are going to be non-polar because the difference there is 0. So H and Cl is the only one that makes sense because H is 2.1, Cl is 3, the difference is 0.9. It will be enough to be polar. So the answer here is B. So once we've talked about polar bonds, we also want to mention how polar bonds can contribute to polar molecules. It doesn't always make polar molecules, but it depends on the geometry. Okay, so a molecule can contain polar bonds, okay, if the two atoms are different electronegativities, but it can still be nonpolar depending on the geometry of the molecule. Now, depending on the geometry here, molecule with polar bonds can be polar or nonpolar. So let's take a look a little bit about geometry. For example, carbon dioxide, when the geometry of a carbon dioxide is actually C double bond O, C double bond O, and it's linear, where carbon points towards the oxygen because oxygen is more electronegative, and you have the exact opposite on the other side, on the right versus the left. You have the electronegativity pointed towards the outside over here. So these two essentially cancel each other out. So overall carbon dioxide, even though it has polar bonds, the molecule is actually nonpolar. Now, that's because it's symmetrical. Now, when the molecule is asymmetrical, like in this case for ammonia, NH3, your N is the more polar side and H is the less polar side, less electronegative versus more electronegative, and then you point towards the nitrogen. So this is the negative N, these guys are the positive N. So overall it's lopsided. In fact, there's another lone pair electrons right here, making it this side so much more electron density than right here. So in this case here, polar bonds in ammonia contribute to a polar molecule. So based on what we've seen so far, anything that's asymmetrical will usually end up with polarity if it has polar bonds. But anything that's asymmetrical will give you a permanent dipole right here, where one side is negative, one side is positive. That means the molecule is also polar. So if it's completely symmetrical, then it will cancel out and then it won't be polar. So we can also signify the dipole moment by drawing arrows. We point the arrows towards the more negative side. So in this case, Cl is more negative, electronegative, density is big, density is small for H. Br, density big, H, small density. And Cl is big density, I is a small density. And if you have water here, O is where the electron density is, H is where a little bit of it is there. Most of it is at O. So these here are showing you dipole moments. So we want to learn about how to draw a Lewis dot structure. So we have some strategies. We will be drawing Lewis dot structure first, and then based on Lewis dot structure, we will determine geometry. But Lewis dot structure does not tell us anything about geometry yet. So let's take a look. The first thing is we gotta count the number of valence electrons, okay? We look at each atom, we count how many valence electron each atom contributes to it, we add them up. And then the next thing is we try to arrange them by connecting each one with a single bond. And you always put the more electronegative atom on the outside, and you put hydrogen on the outside as well. So hydrogen can only form one bond, can never be in the middle, so it has to be on the outside. And you also put more electronegative atoms on the outside. Now, the next thing is you fill in the blanks by adding electron pairs to make sure everybody has an octet. Now, who doesn't have an octet? Hydrogen doesn't need an octet, it only needs 2. Helium only needs 2. Everybody else needs their 8. So that's the octet, the 8 valence, okay? Now, then you count the electrons, make sure they match the total valence that you just calculated earlier. If it matches, then it's good. If it doesn't match, there's too many electrons, we add in double bonds or triple bonds. Each double bond will shrink the electron count by 2. Each triple bond shrinks it by 4. If you don't have enough electron, you can add electrons usually to the central atoms that can have expanded octet. So anybody in period 3 and greater can have expanded octet. Anybody in period 2, period 1, they cannot have expanded octet. Expanded octet means more than 8 electrons. So you fill in the blanks and you add in double or triple bonds as needed to make sure everybody has an octet, that they're happy, and make sure the electron counts match what you just calculated. So we talked about how double bond shrinks it by 2, triple bond shrinks it by 4. Alright, so let's take a look here for NF3. We need to draw the electron Lewis dot structure for it. So number 1, let's count the electrons, okay? Nitrogen is in group 5, so it has 5 valence. Fluorine is in group 7, so there's 7 electrons, but there's 3 of them. 5 plus 21 gives me 26. So when I draw the structure, I need to have 26 electrons, okay? So I added electrons, so I know I have 26 total. Let's start drawing. I'm going to put F on the outside because F is more electronegative, N in the middle. So we'll start off here. So N, and then F on the outside. So I'll just draw like 3 F's around it. Remember, we don't know the geometry yet. We're just drawing the bonds. Okay, so I'm going to add single bonds to everybody. Single bond, okay? And then we have to fill in the blanks to make sure everybody has an octet. So if you cover off the entire side here, so right here, all of this is invisible, okay? You're only looking at the F and this bond here. So F and 1 bond here is 2 electrons. So I'm gonna have to draw 6 more to make it have an octet, okay? So that's how I'm gonna draw the F. So now this F here has 8 electrons. I'll repeat on the other F's. That gives that guy 8. And then we'll do this for this guy. That's also 8. And then nitrogen has 6 already around it because it's 3 bonds, right? So I need to only draw 2 more electrons. So now we want to count our electrons, okay? We have 8 plus another 8 plus another 8. So 8 times 3 is 24 plus 2. That gives me 26. So this drawing is correct, okay? Electron counts match. We start with single bonds. We fill in octets. If it works out, but the number is the same, that's good. But remember, we're just drawing the Lewis dot structure. We don't know the actual geometry yet. We'll talk about geometry in a little bit. So let's try drawing for CH2O, okay? CH2O, where what you want to do is H will go on the outside, O will go on the outside because they're more electronegative. I'm going to put C in the middle. We count electrons here. Carbon is in group 4. Hydrogen is in group 1. There's 2 of them. Oxygen is in group 6. So 4 plus 2 plus 6, that gives me 12 total. Okay? Well, when I draw, I'm going to make sure I have 12 electrons. But let's start. So I said hydrogen will always go on the outside. So we'll put 2 H's. And then we'll put an oxygen on the outside as well. So we always start with single bond, okay? And now hydrogen has 2 electrons already, so we don't need to draw anything on it. But oxygen here, you'll need 6 more because there's 2, and then the 6 electrons around it. Now carbon has 3 bonds, so there's 6 electrons already. So I only need to draw 2 more. Okay, so let's count my electrons. I have 8 right here, okay? And I have 10, 12, and 14. You're like, oh, wait, I have 14 electrons here, but I only need 12. Okay, so that means this is wrong. I have too many electrons that I drew out. So remember, to shrink the electron count, we only need to shrink it by 2. We add a double bond. And remember, we cannot add a double bond on hydrogen because they can only hold 2. We'll put a double bond with the oxygen here. Okay, so I'm going to redraw it here. Right here, we're going to do C, H, H. But in this case here, I'm going to add a double bond with this oxygen. So if you see when you add a double bond, the carbon already has 4 bonds. You don't need to draw a lone pair on carbon anymore. So all you have to do is there's 4 electrons in the 2 bonds for oxygen. So 4 plus 2 is 6, plus another 2 gives you 8. Now let's count our electrons. We have 8 in the middle, right here, and then 10, 12. So yes, this one would work. So this is the correct Lewis dot structure for CH2O. Okay, so always try to put carbon in the middle, H and more electronegative stuff on the outside. And each carbon can hold up to 4 friends, so it can easily hold 3 guys around here, 1, 2, 3. So if it could hold an extra one there too. So carbon can have up to 4 friends. Okay, so that's how you draw CH2O. So let's draw for carbon monoxide the Lewis dot structure. Carbon is in group 4. Oxygen is in group 6. So I need to draw something with 10 electrons. Okay, so let's start off with C, single bond O. And then because the single bond has 2 electrons per O, I need to draw 6 more around O. Okay, you also count the single bond for carbon because you're always just covering, like if you were looking at carbon, you cover the O up. So you see 1 bond here, so 2 electrons, so you need to draw 6 more. If you were to look at oxygen, you cover up carbon right here. And you'll see that oxygen has 2 bonds, so you need, not 2 bonds, 2 electrons in the bond here. So 2, 4, 6, 8. Okay, that's why you draw 6 around it. So I'm going to do the same thing for carbon. I have to draw 6 to give them an octet. So when you draw 6 though, let's count how many electrons. We have 2, 4, 6, 8, 10, 12, 14. So this one has 14 electrons. Now it looks pretty and all, but this is wrong because this is not the same electron count as what we are after. We need 10. So remember, if you need to shrink it by 4 count, because 14 to 4, you can add a triple bond. You could also shrink the electron flow account by adding 2 double bonds, but we don't have space for 2 double bonds because there's only 1 bond here, one side, right? So we have to be efficient and we have to add a triple bond in the middle right here. Okay, so if you add a triple bond, each one of them already has 6, so you only need to add 2 on each side. Okay, so this will give us how many electrons? Let's count. 6, 8, 10. That's perfect. This is 10 electrons. So this is the correct Lewis dot structure for carbon monoxide. Next, we want to look at another Lewis dot structure. We want to look at the Lewis dot structure for NO2 negative. Okay, so we got to do NO2 negative electron count first. Nitrogen is in group 5, oxygen is in group 6, and then because there's a negative charge right there, we will actually need to add 1 more electron to electron count. So what we get here is 5 from group 5, 2 from group 6, plus 1 for the negative charge, and we get a total of 18 electrons. So when you draw, you need to make sure your structure has 18 electrons. Everybody has to have an octet and happy. So let's start. I'm going to put nitrogen in the middle, oxygen on the outside because oxygen is more electronegative. Based on the trend, when you go from left to the right, oxygen is more electronegative. So O is going to go on the outside. I'm going to do N in the middle, okay, and then O on the outside. Okay, so I'm going to always start with single bond just to see where it goes and then fill everybody with an octet. So I have to draw 6 on that guy. Nitrogen already has 2 bonds, so I need 4 more. Oxygen has 1 bond, so I need to draw 6 more. Okay, so that would be what I have to draw. And let's count how many electrons I have. So right here, I have 8, okay, plus 2, so 10, 12, 14, 16, 18, 20. You're like, wait, 20 electrons, that's a lot. So this is 20 electrons, okay? That's a lot. We only need 18, so we can't have this. That's too many. How many? We got 2 extra, okay? So to shrink it by 2, we put a double bond in. Remember we said we can, if you add a double bond, you can make it go down by 2. Now the question is, where are you going to put your double bond? Are you going to put it on the left side or on the right side? So if you can't make up your mind, because there's no reason to draw on one side versus the other, you have to draw both options out, okay? So my both options are going to be N to O, one side is double bond, okay? So this side I will need 6 more electrons. Nitrogen has 6 that are bonded because there's 3 bonds, so I need to draw 2 more. And then this guy already has 2 bonds, so I only draw 2 more lone pairs. So that will give me the correct electron counts. So this will give me 18 electron right here. Okay, if you count, there's going to be 18. Now, and then we go over here, you're like, well, you know, we already talked about how you can't decide where you want to put your double bond. So we draw both options out. This time we draw my double bond on the right side. And then as usual, you fill in your octets. Okay. And because it's charged, I put a bracket and put a charge on the outside. This is also 18 electrons. That's how you would draw it for NO2 negative. And in this case here, nitrite ion has 2 resonance structures. So these 2 here are called resonance structures, where your electron configuration is slightly different because one side, like you can't basically, one side has 2 bonds here, one side has 2 bonds on the opposite side. So one's on the left side, one's on the right side, and these 2 are resonance structures. So earlier we were drawing resonance structure for nitrite ion here, NO2 negative. We said there are 2 places we can put the double bond, so we drew up both options here. Okay, so a little bit about resonance structures here. The actual molecule is not going to be half the time like this, half the time like this. It's not going to be 50-50%. It's actually a hybrid of both these resonance structures. If you were to crystallize NO2 negative, you would see that The bonds between N and O and N and O here, because half the time is double bond here, half the time is double bond there, but that's not the real structure. The real structure actually has NO bonds. Two of them are identical bonds, but each one has a character between a single and a double bond, single and double bond here, just to hybridize our resonance structure. So resonance structure doesn't tell us that a certain percentage of the time it stays over here, a certain percent it stays over here. It's actually just a representation of your options you have. And true molecule is a hybrid of a resonance forms. So in this case here, you'll have the true structure is two identical oxygen with the characteristic between a single and a double bond. So usually it's about 1.5 bond character. So next we want to draw a little bit for carbonate ion here. Carbonate is CO3 2 negative. We want to draw the Lewis dot structure. So carbon is group 4, and then we got 3 of oxygen from group 6. And then because it's 2 plus here, it's 2 more 2 negative, so it's plus 2 electrons. So in total here you get 24 electrons. Okay, so when you draw, you want to make sure you have 24 electrons. I'm going to put the carbon in middle, oxygen on the outside because oxygen is more electronegative. So let's try it out. So carbon, oxygen, oxygen, oxygen. Okay, always try with single bonds and then you fill in your octets and see how many electrons we have. Once you get good at it, you don't have to always try and do like trial and error. You'll be able to draw it straight. But I just wanted to show you how the process is. So you start with single bonds and then let's count our electrons. My electrons here, I have 8 plus another 8 plus another 8. So that's 24 plus 2. So I actually have 26 electrons. That's not good because I have too many electrons. I need 24. So that's no good. So what I need to do is put a double bond in because that will shrink my electron count by 2. When I put a double bond in, I can't decide which bond to put a double bond, so I draw all 3 options, remember, all 3 resonance structures. So let's draw it out. C, so we start a double bond on this side first, and then we fill in our octets. And you don't need the carbon lone pair anymore because now it has 4 bonds, so there's only octet. So this is one option here. Because it's charged, I'm going to put the 2 negative charge on the outside. So that's one resonance structure. My next resonance structure will be my double bond going to the other oxygen. And then we'll fill in the octets. And you can always count electrons. You will see that it has 24 electrons right here. Just because it's we added a double bond, so the carbon doesn't need a lone pair, so you end up having 24 electrons. So our next resonance structure will be the double bond on the right side. And then we'll fill in the blanks with octets. And that should be it. The structure for carbonate. Lewis dot structure. A really cool fun fact about compounds, ionic compounds containing polyatomic ion, is that polyatomic ion is an ion, but it's actually due to covalent bonds. Because CO3 2 negative, we just drew how the bonds were, and this one has covalent bonding in there, but it's charged. So it has covalent bond here and it's ionic bond over here. So it has both ionic and covalent bond inside a compound like Na2CO3. So let's talk a little bit about geometry. Geometry is based on the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. So basically the valence electrons and they are repulsing each other, so they need a lot of space to maximize the area they take up. Okay, so they'll spread the furthest they can away from each other in a 3D dimension. So over here, molecules adopt geometries to minimize electrostatic repulsion between pairs. So that means they take up as much space as furthest away from each other as possible. Here are some of the common shapes that you'll see. You'll see that water is a bent shape. We call it bent. And then linear for carbon dioxide. And this guy here is like a triangle but flat on a plane. So we call it trigonal planar because plane, one plane. And the other one here is tetrahedral. So tetrahedral is shaped like a tetrahedron. So this is for 4 groups. This is for 3 groups. This is for 2 groups. And this one here, water, is actually based on the tetrahedral form. Here, you see how this part here kind of looks like the part of the tetrahedral? That's because it's related to that. So these are just common shapes that we have, okay? So water shape, molecular shape is actually called bent V shape, same thing. So we'll first start by looking at linear geometry and trigonoplanar geometry. Linear geometry is when you need to spread out 2 electron pairs, or we call it electron groups, okay? 2 electron groups around a central atom. So if beryllium has to spread out Cl and Cl, it's like beryllium likes Cl and this he likes the other Cl, but then the Cl and the Cl can't stand each other, so they need a lot of space away from each other. So how do you spread them out? Like a friend taking like a person taking 2 friends to a party, but these 2 friends can't stand each other. They'll each hold your hand, but be 180 degrees away from each other. Okay? So as much space as possible away from each other, basically. The best way to spread out 2 groups is to spread out by 180 degrees. So that's how you get a linear geometry. Now, if you have 3 groups here, the best way to split up 3 groups, you would actually split them 3 of them all on a single plane, 120 degrees from each other. So it kind of forms a triangle, and that's how we get trigonal planar here. So this is if you have boron and you need to have 3 friends, you spread them 3-way, you get 120 degrees away from each other. Now, on the other hand, if you have 4 groups, like CH4, and you need to spread all 4 out as far away from each other as possible, you actually spread them out over 3D, and it's 109.5 degrees away from each other. So if you took a look, it's like this is one part of it, that's the other part, that's the other part. They're all 109.5 degrees away from each other. You see how they have a tetrahedron shape here? That's where the name tetrahedral geometry comes from. Okay, so CH4, CCl4, anything that's like CF4, those guys will all have tetrahedral geometry. Now what happens when you have a lone pair? So like ammonia here, when you draw them out, it's NH3, and then you have a lone pair up here. So it's 1 bond, 2 bond, 3 bond, and then you have a lone pair. So what happens is the lone pair counts as a group. So there's 4 groups, 1, 2, 3, 4. So you spread them out as tetrahedral at first. But because the lone pair here is not really an atom, it looks kind of invisible. So what happens is it looks like a tetrahedral shape, but this guy is a lone pair, so it's not really there, it's just electrons. So the molecule looks like a weird, like a little pyramid right here. Okay, so in this case here, we have 2 different geometry names here. The electron geometry, based on 4 electron pairs, electron groups, is called tetrahedral. But because one of them is a lone pair, the geometry considering only the bonding electrons on the molecule with atoms is called trigonal pyramidal. Let me add the trigonal on the top. That's because it looks like a little pyramid. The N is on the top, and then you have like 3 H's on the bottom. So when I draw my H, this one sticks out from the paper, this one goes behind the page. So that's kind of how I tell them apart, but that's what it will look like. And then this lone pair here is like invisible, you can't see it. So it looks like a little triangle, and it's like a pyramid top. So it's trigonal pyramidal. Now, if you have water, like earlier we saw it was bent, right? Like a V shape. What happens is water, when you draw the Lewis dot structure, is four groups around oxygen. So four groups. So the base level here for electron geometry, looking all four pairs here, is tetrahedral. So you have the shape of tetrahedral, but then two of them are invisible. This one's invisible, that's one invisible. So then it looks just like a V shape, a bent shape, because it's not straight. Okay, so the geometry, the molecular geometry is bent. The electron geometry is tetrahedral because it has four groups. So to determine molecular shape, number one, we need to draw the Lewis dot structure. And then we count how many electron pairs and we arrange them to minimize the repulsion. So we spread them out as far away as possible from each other. So in this case here, you always have to pick out the central atom and we see how many electron pairs there are around the central atom. And then we pick the geometry that's best suited for it. So I have a series of tables that's coming up that will show you more in detail what the electron geometry. So remember, first we draw the Lewis dot structure. We look at all the electrons in there. So we have something called electron geometry. And then we look at if there's lone pairs, the lone pairs are invisible, then we have something called the molecular geometry. So what counts as an electron group? So let's write it down. Electron group can be, number one, really obvious, is a lone pair. Okay? And then it can also be any type of bond. So a single bond is one group. A double bond is also considered one group. A triple bond is also considered a one group. Now sometimes it's not a lone pair, it's just one electron. We call it a radical electron. That's really rare. But these are the electron groups. Okay, so when you draw a Lewis dot structure, and then you count how many lone pairs or how many single bond, double bond, triple bond, radical electron around that central atom, the atom in the middle, and then you look at this table here, okay? So you will want to memorize electron groups for 2, 3, and 4. So this whole entire slide and the next slide you will have to memorize. But once you have group 5 and group 6 electron groups there, you can wait to memorize that for a later class. So let's see. Electron groups, if you have two groups, okay, and all of them are bonded, there are no lone pairs. So when there's no lone pairs, the electron geometry and the molecular geometry is identical. That's because there's no lone pairs that are invisible, making things look funny. Okay, so electron geometry and molecular geometry identical because there's no lone pairs, and it's linear like in the example of carbon dioxide we drew out. See, why do we say carbon has two groups? Because there's double bond, one group, another double bond, another one group. So there's two groups here. You spread it out, it should be linear. If you had three groups and all three of them are bonded, there are no lone pairs, it would be like this example for BF3. One group, single bond, single bond, single bond, three groups here. So you would spread them out over here. And the bond angle from here to here, here to here, here to here is all 120 degrees. So they show you the bond angles here as well. So that's kind of nice to have it in a table all together. Okay? Now, because there's no lone pairs, these two are the same. Electron geometry and molecular geometry is identical. It's called trigonal planar because it looks like a little triangle. It's on one plane. Now, if you had a lone pair, like in this case here, SO2, we would draw it out. You have a lone pair, so one group, two groups, three groups, but one of them is a lone pair, so it's two bonding groups and one lone pair group. So that will give me a weird shape because this top electron here, this part here is invisible. So you see how they drew it without that now? So this is why this is called bent shape. Okay, so molecular geometry is now bent even though the electron geometry is trigonal planar because electron geometry considers in the lone pair, molecular geometry, the lone pair is invisible, you can't see it. so then it looks bent. Now every time you have a lone pair, it squishes the bonds closer together. So if it was 120 without lone pair, with a lone pair it will be less than 120 because it got squished closer together. That means this bond angle here maybe is around 118 instead of the 120 up here. Okay, now let's take a look at four groups. For groups, we say we would spread it out like a tetrahedral. Okay, so if I were to draw it, these two are on the same plane, and this one's sticking out from the paper, this one's going behind the paper. Okay, so that's why earlier I had a picture where a thick wedge and a hash wedge were sticking out of paper and going behind the paper. So in this case here, we have 4 and 4 and 0 because all four bonds are bonding group, and there's no lone pair. So the tetrahedral stays for electron geometry and for molecular geometry, and the bond angle is 109.5. So from here to here, 109.5, 109.5, 109.5, 109.5. Okay, so make sure you memorize all this information here for this first slide. And let's take a look at more examples here for our groups here. So you'll have to know the 4 electron groups. The 5 electron groups is not as common in our class, so you can always refer to it when you have homework and quizzes, since it's something you can still refer to. But you should try to memorize at least for the first up to 4 electron groups. So if you have 4 electron groups and 3 of them are bonding, 1 of them is lone pair, like in this case of ammonia, you see how it still looks like a tetrahedral, but the top part is invisible now. So this becomes a trigonal pyramidal, a triangular pyramid, okay? And because there's a lone pair, it's going to be less than 109.5, so this is probably around 107 right here, 107 right here. And if you take a look at water, it has 4 groups. 2 of them bonded, 2 of them are a lone pair, so 2 and 2. So my bond angle now is based on 109.5, but it's going to be smaller. So if this is 107 because of 1 lone pair, this probably will be around 105 because of 2 lone pairs. So because this guy is invisible, and then this one is invisible right there. Okay, so that gives you bent. It looks just like the bent structure. And then we can take a look at 5 groups. 5 groups are called trigonal bipyramidal because to spread out 5 groups, you have 120 in the middle, like a trigonal planar and a linear combined together. So this is 120, 120, 120. But from here to here is 90, here to here is 90, because this is like a linear plus a trigonal planar combined together. Okay, so that's why we have 120 and a 90 degrees bond angles here. If it's no lone pairs, both of them, electron geometry and molecular geometry, we'll call trigonal bipyramidal because it looks like there's 2 pyramids. See a triangular pyramid on the top and a triangular pyramid on the bottom right there. And then let's take a look at electron group for 5 when you have 4 bonding and 1 lone pair. So you see here, this is when we have expanded octet here for 5 groups, right? So you see how we have 1, 2, 3, 4, but 4 of them are bonded, and then there's a lone pair here, SF4. So in this case here, there's this group that was missing here. The reason why it's missing from the 120 is because 120 has more space than if you were to get it out of a 90. So you always remove the 120 bonds first to put the lone pair here. So in this case here, trigonal pyramidal, bipyramidal is the original electron geometry. You take away 1, now it looks like a seesaw. If you imagine this to be the floor of the playground, you put a kid right here, put a kid right there, you can do a seesaw shape. So that's a seesaw. Okay? Now, again, the bond angle is going slightly less than 90, slightly less than 120, just because of the lone pair here, pushing these guys closer together. And then we have, if you have 5 groups with 3 bonding and 2 lone pairs, like this case here, 3 bonds, 2 lone pairs, you would take out another one of these guys here, okay? So then you have 1, 2, 3, a T shape left over. And the bond angle now is 90 degrees because you've taken out 2 of the 120s. So you have only 90 degrees bond left right there. And then if you have 2 bonding in 3 lone pairs, 2 bonds and 3 lone pairs here. You take out another guy, you take out this guy, another 120 here. Now you have 180, so you have linear in your molecular geometry. So you see here the molecular geometry. Seesaw is like, it literally looks like a seesaw. T-shape, it looks like a T. Linear because it looks linear. The geometry name always resembles what the shape is. If you had 6 groups, you start with 6 and 6 and 0. So if you drew SF4, in this case here, you have 6 groups, all of them are bonded. The best way to split 6 groups is to split them 90 degrees. So instead of 120 like the 5 groups, you just add another group here. This is also 90, 90, 90. So there's 6 groups altogether. Everybody's 90 degrees away from each other. This is the shape of octahedral. Okay? Now, if you had 1 lone pair and 5 groups, you would take the lone pair, put it on one of the groups here. So you see how this is invisible? Now, it looks like a little square, but if you connect the dots, it's like a pyramid. So it's square pyramidal for the molecular geometry. Octahedral is still named for electron geometry. And of course, the angle is less than 90 because this lone pair is squishing these guys closer together. Now, if you have 6 and 4 and 2, you have 2 lone pairs here. What's cool is you take off another guy, one of this here, up here. Now you have just the 90 degrees left behind. So this is called square planar because it's on a square, it's on one plane. So what is the molecular geometry for CCl4? Let's draw CCl4. CCl4 looks like this. So you have 4 plus 4 times 7. Okay, so that should give me a total electron of 32. Okay, so if you draw them with 32 electrons, I would put Cl, 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 Cl. So you always draw the Lewis dot structure first just to see how many groups there are. Let's see if it matches. If I fill my octets in, do I get 32 electrons? Yes, because 8 times 4 is 32. So this Lewis dot structure is good. So that means, how many groups does it have? It has 1 group, 2 group, 3 groups, 4 groups. None of them are lone pairs. So if that's the case, none of them are lone pairs. So what you do is you have a tetrahedral shape, right? So that's tetrahedral. So if we were to draw it out in a tetrahedral form, this is how I would draw it. I would put a carbon in the middle, 1 Cl here, 1 Cl here, because the bond angle is 109.5. And then the other Cl sticks out from the paper. And the Cl goes behind the paper, or the screen in this case. Okay? And that would be how we represent it. The next one here, we want to take a look at if CCl4 is polar or nonpolar. So we know it was tetrahedral and it was symmetrical, wasn't it? It was like this, symmetrical. So they should cancel each other out, okay? So the CCl4, they cancel each other out because they're completely symmetrical in 4 directions. So that means it's nonpolar. So C would be our answer. Okay, so CH2O for formaldehyde, we drew it earlier, but let's take a look at the geometry and if it's polar or nonpolar this time. CH2O earlier when we drew it, we said C and then we have H and then H. And then we had to put a double bond on the O because we had too many electrons if we drew it another way. So you can go back to the previous slides too and take a look if you forgot. So our electron count here should match because we have 4 plus 2 plus 6, we get 12 electrons, and if you count 8 plus 10, and 8, 10, 12. So yes, this is 12 electrons. So how many groups do we have? We have 1 group, 2 group, 3 groups. Okay, so 3 groups, that means we have trigonoplanar as the geometry. So if you were to draw it in the geometry, it would be like, I'll just put the O here and then the H over here. So, okay, and then this angle is 120 away from each other. Now, is it polar or non-polar? Let's take a look. In this case, oxygen is more polar, more electronegative than carbon, so it points up to the oxygen. C and H are non-polar bonds. So in that case, the O side is negative, the H side is positive. So yes, it is polar. Polar bond and polar molecule. Because it didn't cancel out. Because even though these two guys on the bottom are non-polar, but this bond here is polar. So that's enough to make the molecule polar, because it's not symmetrical, because there's O on this side and H is on this side. So what's the molecular geometry for NH3? Is it polar? NH3 would be 5 plus 3, so we get 8 electrons. So if you were to draw it out, you would have NH, H, H, and then a lone pair. That would give you 8 electrons. So we have 4 electron groups here because there's one group, 2 group, 3 groups, 4 groups. So the base shape here will be tetrahedral. So let me redraw in a tetrahedral form. So if you have N and a big lone pair here, 1H this way, 1H sticking out, 1H going backwards in the screen. Okay, and our bond angles here are slightly less than 109.5. Same here. Okay, all right, so we have that, and then that shape here, the electron geometry would be tetrahedral, but because the lone pair is invisible, this guy is invisible, so that means it looks like a little pyramid, right? It will be trigonal pyramidal. So let me add the trigonal here. So it will be D. D is my answer. Is it polar? Let's take a look. So nitrogen is more electronegative than hydrogen, so it points up, points up, points up. And then there's an electron here. So really the nitrogen side is really electronegative, the partial negative side, and this is partial positive side. So yes, it is polar. And you can see the lone pair threw the symmetry off, so it's asymmetrical, so it's polar. Polar bonds and polar molecule. So the next one is molecular geometry for CO2. Is it polar or non-polar? So let's draw CO2 out. C is 4 plus 2 times 6, so we get a total of 16 electrons. Okay, so we have to draw 16 electrons here. What you have to do is put the carbon in the middle, oxygen on the outside. And you'll see that if you drew just a single bond, we can try a single bond and see. You'll have 20 electrons. That's way too many, right? Because you need 16. So let's cross that out. So 20, because let's count. There's 8. There's another 8. So that's 16, 18, 20. Okay? So that's 20 electrons. So whenever you want to shrink it by 4, I'm going to put in 2 double bonds. So each double bond shrinks it by 2, remember? So CO and CO. And the carbon doesn't need to draw lone pairs around it because it already has 4 bonds, it already has an octet. So that's CO2, and you see how the Lewis dot structure tells us there's 2 groups. 1 group, 2 group. So 2 groups will end up being linear, remember? So actually the Lewis dot structure this time luckily happens to be the geometry as well. This is 180. So it's linear. Is it polar or non-polar? So if you see here, carbon dioxide goes this way because oxygen is more electronegative, and the other pulls the opposite. It's kind of like tug of war with 2 people equal strength, 2 groups equal strength. So they cancel each other out. There's no winner. So when they cancel each other out, this molecule has polar bonds, but non-polar molecule. Alright, so this is the end of our chapter.